let's look at how you would calculate the field from an infinitely long wire using the Biot-Savart law. I'm just going to define a coordinate system and some variables. Let's see. So somehow along the z-axis I put a infinitely long wire, or at least long wire, and it has a constant current I. And this was the current density. And I'm just going to put this into the Biot-Savart law and see what I get. And the delta functions, well, you can imagine what those do. So I'll just skip to this. The z hat is the same in the prime and unprimed coordinate systems, right? It's just a constant. This is, here you can see this vector now. Equations get too big, I think. Okay, so this is the R vector, right? The point is, it's, yeah. The z vector prime minus R, that's here, because I'm integrating over a little line elements at the point z prime. This is my little line element now. I'm going to define a couple of angles, just because it's convenient. Right. And S is the distance. So this is a cylindrical coordinate system. S is just a distance from the wire. Theta is a convenient angle. There's a rotational invariance here now. So there's no dependence on the phi in the cylindrical coordinate system. And yeah, z prime is just this point at the line wire element, which I'm currently integrating over. So this is the distance from the point to the line element. And it has the same direction as that vector. Yeah, you can find this. Just put this into this current distribution into the Biot-Savart law from the previous lecture, and this is what you get. Okay, now I make the following observation. This is a unit vector pointing along here, right? And the z hat is pointing along this direction. So I end up with essentially sine of alpha. Right? The length of the cross product is, no, let's see. The cross product is just the length of the two vectors you're crossing and the angle between them, the sine of the angle between them. And that's what we got here. Okay, I also make the following observation. I now spent this guy, so to speak, and two of these. No, one of these. So I'm left with two of them. And that's equal to the following. Right, so that's just basic trigonometrics, right? Get the length of this line. Okay. And then I think if you insert this into this integral, Then you get sine of alpha and cosine of theta s square. You have to integrate over the angle in the end. But I think you can do that as an exercise. It should be quite straightforward. There's of course a connection between alpha and theta, but I'm pretty sure you can do that too. Right. So that's homework for next lecture. Now we're going to look at a small application of Amperes Law, which is standard in all the textbooks, so it's not very exciting, but we have to do it. The Amperes Law looks like this in the magnetostatic regime. I'm now going to look at some area. And I'm going to let current flow through this area. That's my current field, without divergence, of course. Now I'll start off by integrating this equation over the total area to see if I can find some relation with the magnetic field and the current, total current on this area. This, let's see, the integral over all the area times the J is of course the total current flowing through this area. I'm going to call this the enclosed current. It's the current enclosed by the curve circling the area edges, so to speak. That's the right hand side of the Ampere law. And if I integrate the left hand side, well, then you immediately think of, or you should immediately think of the Stokes theorem from vector calculus, and it relates the curl of a vector field, or the line let's say the surface integral of the curl of a vector field to the line integral of that vector field. I hope I got that right. So I'm going to just call it C. Oh, let's see, dA. That's the curve around the area, the edges of the area. And that is H. Like this. Let's see. This is the notation I used. Okay. So what we end up in the end is the following. This is called the Amperes law in integral form. The enclosed current is equal to the integral of the magnetic field flowing, the magnetic field around the current, like this. It makes sense intuitively, right? Because the more current I put through it, the more magnetic field I get swirling around. So for each little current I add, well, the more magnetic field I get. And this can be used if you have radial symmetry. That's the most important use of this, and I'm pretty sure you're already using a similar, something similar in the midterm project, right? You're probably using the Gauss law, which is in electrostatics the law you use when you have some sort of symmetry. Then you can use the Gauss law to find the electric field. Now we're going to use symmetry to find the H field. And the example, which is kind of standard, is the radial symmetric current distribution. I'll put a point here. I have some sort of conductor. I just I don't cut the conductor, of course, because then there wouldn't be any conducting wood there. So I will just look at this. I'm not sure how to say this. I'm just going to imagine a surface there to define the total current. So the total current would be then just the surface integral of the current density. I'm putting the wire on the let's say an axis, the z axis, for example, and I can then find the field outside by symmetry. So first I'm going to look at a point outside. Then of course the total current is just, well, the total current. I don't have to integrate anything. The line integral of the magnetic field would then by symmetry be just the length of the curve around. I'm going to just use my surface is just going to be a plane because that's easier, right? That conserves the symmetry, so to speak. So it's just the length of a path around, let's say an imagined path or curve around the wire, on the outside of the wire, times the so far unknown magnetic field. So by using this law, I could just write down the H field. There's a phi hat here because, well, it's the right-hand rule. I hope you all remember that. You put the thumb along the wire in the direction where the current is heading, and then the fingers show the direction of the field. I wrote R here, but it should be S, of course. Right. So, why is this so nice? Well, over there we spent a lot of time doing integrals, and we got them all wrong anyway, at least if we didn't have the lecture notes. But here you could just stare a bit at the problem, and because we can exploit the symmetry, the answer more or less gives itself. Now I want you to think about at home, what happens if, well actually, why don't you discuss with the guy next to you for 5 minutes? What happens if you're inside? How would you solve that? How would you change this approach, this sketch I made? You got 3 minutes, and then come up with some answer. And if no one has the answer, then we discuss some more. Well, since you're all quiet, I can only assume that you have an answer. Hands up. Now this is ridiculous. Come on.
I'm not certain about this, but I seem to remember something about in a conductor, the charges will move along the surface of the conductor, not in the middle.
Right.
If that is correct, then you wouldn't have any ion flows.
Okay, that's a good comment. That's a good comment. I didn't think so much about that. We just put some current distribution in, let's say, a vacuum. You could actually have this, let's say, in a particle accelerator. And then you would just have this distribution, and we don't worry so much about the materials. Let's just say that we manage this somehow, even if it's unrealistic. How would you solve it mathematically inside the conductor? No, there is no difference really, right? Except that so far we looked at the point outside, but if you're inside, just integrate up to some smaller radius. And then there's going to be a dependence here. So this is going to be, the current is going to be, well, yeah, you just integrate out to that point and then you have the field. So that's essentially what you're doing in the midterm project if you're doing it cleverly, right? So there you got a hint for that as well. Okay. Now let's look at the magnetic vector potential. Right, we remember from electrostatics that we can define, because the E field is curl free in electrostatics, we can define the electrostatic potential, the scalar potential, in the following way. Because the potential is in fact a scalar quantity, it's somewhat easier to work with than the electric field. Now for magnetostatics it's going to be slightly harder, because now it's not a curl-free field, it's instead a divergence-free field. But then we can write the B field as the curl of a potential. Like this. So this is called the magnetic vector potential, or just a vector potential among friends. So we'll see if we can find some easier equations for the A field than we can for the B field. Because as you can see, as you can remember from the last lecture, we had a lot of cross products, integrals. It's kind of messy. So let's hope that the A field is somewhat easier to work with. Now the first question, of course, is what are the equations for the A field? And then we start out by looking at the Maxwell equations, as always. This equation is now baked into A immediately, because, well, the B field is the curl of the A field, and the curl of, well, let's see. If I may now take the divergence on both sides, the curl, no, the divergence of a curl is always 0, right? So this equation is automatically fulfilled, because we can write it in the following way. The same happened with the E field, right? There's no curl of the E field. So when we take the gradient of a scalar, well, then there is no curl. The second equation is, of course, the Amperes Law. Which looks like this. Yep. So I'm going to now insert this relation into the B and see what happens. And if you did the exercises and if you have a good memory in addition, you'll remember that this turns out to be the following. I'll take the curl of the B field, which is the curl of the A field, so the curl of the curl. Well, that's a big mess, but you all learn how to use the Levi-Civita tensor. And but now you realize the usefulness of that, because you can easily show this relation using that tensor. Now, I'm going to make a choice, because you remember in the potential V, we could always make a choice. I could always add a constant to the potential. And now I'm going to say that this term is 0. This is not always true, it's just my choice. And then we're just left with the two terms on the right. I'm going to discuss this more in a few seconds. But for now, let's just accept that. And we're left with the following. This is called the vector Poisson equation. Essentially, each component of the vector A fulfills this equation as a scalar field. So it's just for each component we have a Poisson equation. And that's about all there is to say about that. It looks exactly like the scalar potential, right? It fulfills the Poisson equation, except there's only one component, so to speak. Now, the next question is, of course, why can we choose the A field to have no divergence? It seems crazy, right? Okay, and to prove that, you start off by just considering the following. Now, what if I add a term to the vector potential? So I make an A prime, which is the old A, the original vector potential, which I know is correct. And I add the gradient of a scalar. Can anyone see where this is going? Do they realize why I can do this before I start doing all the math? Any suggestions? Yep. That's exactly the idea. That's very good. So now I'm going to calculate B prime just to show that the gentleman was right. And B prime is just a nabla cross A prime, of course. The first term is just nabla cross A. And the second term is the curl of a gradient, and that's 0. So I'm left with just B again. Just as he said. And there we go. He spoiled the fun of the proof, but it was right. And this is called, when you choose the phi, it's called a gauge transformation. Gauge transformation is just a clever choice of V or A, or a combination of them. As we get to time dependence, the electric and the magnetic field will start to couple through the time dependent terms. And then we'll see that we can choose, we have some freedom of choice in A and V, but we have to make it consistent with the two. But of course, as we're working in magnetostatics, we can just choose freely the A field because V is just, it's not important. There's no electric field, so we just neglect that part. So as we get to the time dependence, it's going to be a bit more tricky, but not much. This is the general idea. So it's all about choosing a clever gauge, which makes it easy for us to solve whatever problem we're working on. And right now, I got rid of this term. I got this equation, but it's only valid in the gauge where there's no divergence of A. I could choose A differently, but I'm not going to, just because it's convenient. The same way you choose a constant of the potential, which reduces the, let's say, the number of terms you have in your equations. And this is called this particular gauge is called the Coulomb gauge. As you get to more sophisticated quantum mechanics, for example, you'll see that you don't only have the vector potential, but also the potential and time dependencies. And then the choice of gauge actually seems to matter. I mean, now you can show that it's not a part of the physics, right? We just choose this this gradient to be 0, but it doesn't change the physics. But in quantum mechanics, it turns out you have to be a bit more careful. The gauge choice should still be unimportant, but it's kind of hard to see because, well, you'll see that in a quantum mechanics course. But this is actually important even for, let's say, not electrostatics and magnetostatics. It's actually important in other fields as well, other areas of physics. Right. Yeah, so the time dependence will couple these, and we'll discuss that later. Okay, as we can see here that the Poisson equation is fulfilled for each component, and we know the answer to, well, we know a solution of the Poisson equation for the scalar potential. And this means I can just write down the solution for the vector potential as well. This is, of course, just because they're mathematically identical, then the solution is going to be the same. Okay. It starts out the same way, except there's a mu naught instead of an epsilon. Can you guys read this? It's okay? Oh, well, no one's complaining. And the figure is as before. Like this. So now, because each component fulfills the Poisson equation, then each component will also have the same solution as the Poisson equation, and then I just might as well write it on vector form. So to do this integral, you just look at each component, and it's the same as doing the integral for, well, for the scalar potential or with the charge distribution. So I'll just write that down for you to compare. As you can see, they look just the same, except that in the Gauss law there was an epsilon, and in the Amperes law there was a mu, and it's on the other side of the division sign. So we just end up with the same because the mathematics are the same. Alternatively, you can get to this result by starting out with the Biot-Savart Law. You just start up with the Biot-Savart Law, and you show that, well, I think I'll just show you how to do that. All right. So first of all, we just write down the Biot-Savart Law. There's the constants. G3R. Like this. Now if you stare at this for a while, you can realize the following, that this cross product, I can write this as the nabla cross of something. We did something previous with the divergence in the case of the scalar potential. like this. All right, so we start out by looking at the Biot-Savart law, and then I'm saying that, okay, I see that I can write this as the curl of something. This integral is the stuff inside the integral is the curl of something. It's the curl of this, and because this is essentially partial derivation, I can move it outside the integral sign. And then, of course, I know that, well, if the B field is equal to the curl of something, well, then that something is, of course, the vector potential. And that's that. So if you stare at this, you'll see that this one is the same as the one over there if you take away the curl. And then we reach the conclusion we wanted to reach. Okay. I think the last thing I'll do today is just to state the boundary conditions for the B and the H field. I'm not going to prove them because we'll get a bit more into the details, I think, when we get to materials. As you saw with the electrostatic case, the boundary conditions make more sense when you start looking at the materials, because usually you need the boundary conditions for the layer between two materials, what happens to the fields there. The BC is, of course, the boundary conditions. And you can write them both in terms of the B and the H field, or in terms of the vector potential. So B2 and B1 is the field. I'm taking the limit value now, so I'm starting out here. I'm going down towards the boundary. I'm looking at the B field here. I come from the lower side and look at the B field at the point just at the other side of the surface, just as I did with the electric fields. And this is the result. You can prove this by looking at the Gauss Law, of course. It's the same as saying this, because if I make an integral over a small box here, there's no charge inside, so, well, home exercise. Here now, in the other boundary condition, there's a discontinuity because of the surface current. The surface current is very well explained in the book what that is. It's essentially the same as the volume current, except you have a delta function across the surface, so to speak. So it's a current running on the surface. Let's say you have, instead of having a round wire, you have a flat, thin one. Then you have a surface current on each side, right? It's the same thing. Okay, and if we look at the vector potential, the one, of course, follows from the other. Then we have the following. Just as with the scalar potential, the vector potential is continuous across the interface, but the normal derivative is not quite. This case, of course, followed from the source term in the Amperes Law. The nabla cross H is, of course, equal to the current density, and then this leads to a discontinuity in the normal derivative of the vector potential and of the H field. And we'll revisit these again when we get to materials, because of course I now assumed something about the material which doesn't quite hold in general. But it's essentially the same as we did with the dielectrics. If you assume them to be linear, which is quite often the case, then the H and the B are proportional. So, anyone have any questions about magnetostatics? I think now is a good time to ask. I'm pretty sure someone has a question. All right, I'll let you think while I wipe the board. Nothing? Okay, I'll see you Wednesday.